Hello there, and welcome to the Sleepy Science Facts channel. Tonight we will be drifting into something closer to home, yet no less mysterious. The Earth is a living, breathing, restless planet full of wonder and secrets. It holds ancient oceans locked inside its rocks, forces so slow we cannot feel them yet powerful enough to move continents, and a history so vast that all a human civilization fits into the final fraction of a single second of its story. Beneath your feet right now, iron is spinning and churning. Mountains are inching upward. Rock is melting and rising and cooling and sinking in a cycle that has never stopped. This is a place where time moves on scales that make the mind go quiet, where the familiar becomes extraordinary when examined closely, and where every layer of ground holds a chapter of story that began 4.5 billion years ago. After centuries of scientific study, our understanding has deepened, yet certainty always remains just out of reach. From the fiery birth of the planet to the slow unraveling of its possible futures, the Earth invites curiosity without ever fully revealing its hand. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow and allow the day to gently fade away as we explore the mysteries of the Earth together. Let's begin. The Earth is 4.5 billion years old, and that number is almost impossible to hold in the mind. To put it in some kind of scale, if the entire history of the planet were compressed into a single calendar year, the first bacteria would not appear until late February. Complex animal life would not arrive until mid-November. The dinosaurs would appear on December the 16th and vanish on December the 26th. All of recorded human history, everything we have ever written down, built, or remembered, would occupy the final 17 seconds of December the 31st. The age of the Earth was not always known. For most of human history, estimates range from thousands to millions of years, and the true depth of geological time was only established in the 20th century through radiometric dating of ancient rocks and meteorites. The oldest known minerals on Earth, tiny crystals of zircon found in Australia, have been dated to over 4.4 billion years. They formed when the surface was still cooling from a molten state. Every rock you have ever stepped on carries within it a piece of time too large to truly comprehend. The Earth did not form quietly. It was built through violence. In the early solar system, the region where Earth now orbits was a crowded place filled with rocky bodies of all sizes, colliding and merging over tens of millions of years. Each major collision added mass and heat, and the accumulating planet grew hot enough to melt entirely. This allowed heavier elements like iron and nickel to sink toward the center while lighter rock floated upward, forming the layered structure we have today. The process is called differentiation, and it gave Earth its dense metallic core, its rocky mantle, and its thin outer crust. The heat from those ancient collisions is still leaving the planet today, contributing to the warmth that drives volcanism and plate tectonics. Earth's formation was not a smooth assembly but a prolonged period of chaos and bombardment, and the planet that emerged from it was almost unrecognizable compared to the world we inhabit now. The quiet surface we stand on is the cooled and settled remains of something that was once entirely molten and glowing. The moon was most likely born from a catastrophic collision, and the scar of that event shaped everything that followed. The leading theory holds that roughly 4.5 billion years ago, a body about the size of Mars struck the young Earth at an angle. The impact was enormous, vaporizing rock and hurling enormous quantities of debris into orbit. Over time, that debris coalesced into the moon. Evidence for this giant impact hypothesis comes from several directions. The moon's composition closely matches Earth's outer mantle, suggesting shared material. The moon has very little iron compared to Earth, consistent with the impactor's iron having merged with Earth's core before the moon formed from surface rock. The impact also likely altered Earth's axial tilt, contributing to the seasons we experience today. Without the moon's stabilizing gravitational influence, Earth's axial tilt might wobble chaotically over long periods, producing wild swings in climate. The moon has acted as a quiet gravitational anchor for billions of years, and its presence may have been important in allowing stable conditions for life to develop and persist. Deep inside the Earth, something strange is happening that scientists are still working to understand. The inner core is a solid ball of iron and nickel roughly the size of the moon, surrounded by a liquid outer core that flows and churns. The inner core appears to rotate at a slightly different rate than the rest of the planet, drifting independently on timescales of decades. Measurement of seismic waves traveling through the Earth at different times suggests the inner core's rotation has changed speed and even reversed direction within recent decades. This is not something you would feel or notice on the surface. But deep inside the planet, the innermost part is moving to its own rhythm, slightly out of step with everything above it. The reasons for this behavior are connected to the complex electromagnetic and gravitational interactions between the liquid outer core and the solid inner core. Scientists use earthquakes as natural probes, measuring how seismic waves bend and slow as they pass through the Earth's interior, and those measurements have revealed a planet whose center is far more dynamic than it appears from outside. The Earth's magnetic field is generated deep inside the planet, and without it, life on the surface would face a very different situation. The liquid outer core is made mostly of iron, and as it circulates driven by heat in the planet's rotation, it generates electrical currents. Those currents in turn produce a magnetic field that extends far out into space, forming a protective bubble called the magnetosphere. The solar wind, a constant stream of charged particles flowing outward from the sun, strikes this bubble and is deflected around the planet. Without the magnetosphere, those particles would gradually strip away the upper atmosphere. Mars, which lost its magnetic field billions of years ago, also lost much of its atmosphere and water over time. Earth's field is not perfectly stable. Its strength varies and the poles wander slowly over decades. At certain points in the geological past, the field has weakened dramatically and reversed its polarity entirely, with magnetic north becoming magnetic south. These reversals are recorded in the rocks and happen irregularly on timescales of hundreds of thousands of years. The field is what makes compass navigation possible, and it is also what produces the shimmering curtains of light known as the aurora borealis and the aurora australis. Plate tectonics is one of the most powerful forces shaping the surface of the Earth, and it operates on a timescale that makes it invisible in a human lifetime. The outer shell of the Earth is not a single continuous piece. It is broken into a series of plates, some carrying continents and some forming the ocean floor, all moving relative to each other at speeds of a few centimeters per year. Where plates pull apart, new crust is created as magma wells up from below. Where plates collide, one can be forced beneath the other in a process called subduction, dragging old crust back into the mantle to be recycled. Where plates slide past each other horizontally, the stress builds until it releases in earthquakes. The theory of plate tectonics was not widely accepted until the 1960s and 70s, despite evidence that had been accumulating for decades. The matching coastlines of Africa and South America, the continuity of rock formations across ocean basins, and the pattern of earthquake and volcanic activity all pointed to a planet whose surface was in constant motion. It changed geology permanently, providing a unifying framework that explained features that had previously seemed unrelated. The continents were once joined together in a single vast landmass, and they will come together again. About 335 million years ago, the landmasses of Earth were assembled into a supercontinent called Pangaea, surrounded by a single global ocean called Panthalassa. Animals and plants that are now found on opposite sides of the world share common ancestors from that time, and matching fossil species on different continents were one of the early clues that the land had once been connected. Before Pangaea, there were earlier supercontinents, including Rodinia and Columbia, assembled and broken apart in previous cycles stretching back over 1 billion years. And the cycle will continue. The current plates are already moving in directions that will, over the next 200 to 300 million years, bring the continents together again into a new supercontinent that scientists have already given tentative names to, including Amasia and Pangaea Proxima. The exact shape is unknown because the details of future plate motion are difficult to project so far ahead. But the broad conclusion is well supported. The map of the world is temporary, and the planet has been redrawing it continuously for as long as solid crust has existed. The mantle is not the solid, static rock it might seem to be. Over millions of years it flows. The mantle makes up about 84% of the Earth volume, and lies between the crust and the core. It is made of solid rock, but under the extreme pressures and temperatures of the deep Earth, that rock behaves over geological time somewhat like a very thick fluid. Heat from the core rises through the mantle in slow convection currents, much like the movement in a pot of heated liquid but millions of times slower and more viscous. These currents are what drive the plates at the surface, pulling them apart in some places and dragging them down in others. The exact pattern of mantle convection is still being studied, and there is debate about whether convection operates as a single layer or in two separate layers. Seismic imaging, which uses earthquake wave to build a picture of the interior the way medical imaging uses sound waves to see inside the body, has revealed columns of unusually hot material rising from deep in the mantle called plumes. These plumes feed hotspot volcanoes of the surface, including the chain that built the Hawaiian Islands as the Pacific plate moved slowly over a fixed source of heat below. Volcanoes are not just destructive. Over geological time, they have been essential to making the Earth habitable. Volcanic eruptions release gases from the planet's interior, and over billions of years this outgassing built up the atmosphere and contributed to the water on the surface. Early Earth had very little free water compared to today, and much of what is now ocean may have come partly from volcanic activity releasing water vapor that gradually condensed as the surface cooled. Volcanoes also release carbon dioxide, which is a greenhouse gas that has played a major role in regulating climate over geological time. The balance between volcanic outgassing of carbon dioxide and the removal of that gas through weathering of rock and burial of organic material is one of the long-term thermostats that has kept Earth's surface within a range suitable for liquid water for most of its history. Large volcanic events have also disrupted that balance dramatically. The eruptions associated with the end of the Cretaceous period were enormous, and there's evidence they began stressing ecosystems before the asteroid impact that finished the work. Volcanoes are Earth speaking from the inside, and what they say has shaped the atmosphere, the oceans, and the conditions that allowed life to take hold. Earthquakes reveal the interior of the planet in ways no drill could reach. When rock fractures under stress, the energy release travels outward as seismic waves of different types, each moving at different speeds and behaving differently when they encounter boundaries between layers of different material. Some waves can travel through liquid, while others cannot. By tracking which waves arrive at different monitoring stations around the world and how long they take, scientists can map the structure of the planet's interior in considerable detail. This is how the existence of the liquid outer core was confirmed in 1914, when a geologist noticed that certain seismic waves were blocked from passing through a region of the planet, indicating a liquid layer. The same method has been used to detect the solid inner core, identify variations in the thickness and composition of the mantle, and map regions where cold, subducting plates have sunk deep into the interior. Earthquakes are destructive events that cause immeasurable human suffering, and that aspect deserves to be held with care. But as probes of the planet's hidden interior, they have told us more about the deep Earth than any other tool we have. Every major earthquake sends a pulse of information through the planet that scientists around the world receive and decode. The atmosphere of the Earth is extraordinarily thin relative to the size of the planet. If Earth were the size of an apple, the atmosphere would be no thicker than the apple's skin. Yet within that thin shell, everything that keeps the surface livable is happening. The lowest layer, the troposphere, extends only about 12 kilometers above the surface and contains nearly all the weather, most of the water vapor, and almost all the air that living things breathe. Above it, the stratosphere contains the ozone layer, which absorbs the majority of the ultraviolet radiation arriving from the sun. Above that lie the mesosphere, the thermosphere, and the exosphere, each growing thinner and more tenuous with altitude. The boundaries between these layers are defined by changes in how temperature behaves with altitude, rising in some layers and falling in others depending on what is absorbing energy at each level. The atmosphere is not static. It circulates continuously, driven by differences in heating between the equator and the poles and between land and ocean. Winds, storms, clouds, and precipitation are all part of the circulation, and understanding it well enough to predict whether more than a few days ahead remains one of science's ongoing challenges because small differences in initial conditions can compound into very different outcomes. Lightning strikes the Earth roughly 100 times every second, and each bolt is a brief, extraordinary event. A single lightning strike can reach temperatures around 30,000 Kelvin, which is about 5 times hotter than the surface of the sun, though only for a fraction of a second. The electrical discharge forms when charge separates within storm clouds, with ice crystals and water droplets interacting in turbulent updrafts in ways that build enormous voltage differences. When the charge difference becomes large enough, the air between the cloud and the ground, or between different parts of the cloud, breaks down electrically and current flows in a channel so narrow and so brief that the surrounding air explodes outward as the thunder we hear. Lightning is also a significant source of nitrogen compounds in the soil because the extreme heat in the bolt fuses nitrogen from the air into forms that can be dissolved by rain and absorbed by plants. Some researchers have proposed that lightning on the early Earth may have helped generate the complex organic molecules that preceded life, providing energy to drive chemical reactions in the shallow pools and early oceans where life is thought to have first assembled. The storm is not just weather. It is a chemical factory running on electricity. The Earth has been through at least 5 major mass extinctions, and the causes tell us something about how fragile complex life can be. A mass extinction is defined as a period during which a large proportion of species on Earth disappear in a geologically short span of time. The most famous is the end Cretaceous extinction about 66 million years ago, when the impact of a large asteroid combined with already ongoing volcanic activity brought an end to the non-avian dinosaurs along with roughly 3/4 of all species. But earlier extinctions were even larger. The end Permian extinction, about 252 million years ago, killed approximately 90% of all marine species and 70% of land vertebrate species. Its causes are still debated but are strongly linked to massive volcanic eruptions in what is now Siberia, which released enormous quantities of carbon dioxide and other gases over hundreds of thousands of years, dramatically altering the climate and the chemistry of the oceans. Each extinction was followed eventually by recovery, but recovery took millions of years, and the world that emerged was never the same as the one before. Mass extinctions are not simply catastrophes. They are also, in a dark sense, opportunities, clearing the ecological stage for entirely new forms of life to evolve and diversify. Before animals, before plants, before anything visible to the naked eye, life on Earth was microbial, and it quietly transformed the entire planet. For the first 2 billion years of life on Earth, the living world consisted almost entirely of single-celled organisms. Among these were cyanobacteria, which developed the ability to perform photosynthesis, using sunlight and carbon dioxide to produce energy and releasing oxygen as a byproduct. For a long time, this oxygen was absorbed by dissolved iron in the ocean, producing the banded iron formations we now mine for steel. But eventually the iron ran out and oxygen began accumulating in the atmosphere. This event, known as the Great Oxidation Event, occurred roughly 2.5 billion years ago, and it was one of the most significant turning points in Earth's history. For organisms that had evolved in an oxygen-free world, free oxygen was toxic, and the Great Oxidation Event may have caused a mass extinction of anaerobic life. But it also opened the door to organisms that could use oxygen in their metabolism, unlocking far more energy per unit of food, and eventually enabling the evolution of complex multicellular life. Every breath you take is a legacy of microbes that lived more than 2 billion years ago. The Earth has been almost entirely frozen at least once, and possibly more than once. The hypothesis known as Snowball Earth proposes that between roughly 700 and 600 million years ago, the entire surface of the planet, including the oceans down to the equator, was covered in ice. Evidence for this comes from glacial deposits found in rocks from tropical latitudes, suggesting that glacier reached sea level near the equator at a time when those regions should have been among the warmest on the planet. The mechanism proposed involves a runaway feedback. As ice spread, it reflected more sunlight back into space, cooling the planet further, which caused more ice, which reflected more sunlight until the whole surface was locked. The escape from this frozen state would have come from volcanic activity, which continued beneath the ice and gradually built up carbon dioxide in the atmosphere to levels far higher than today, eventually triggering a runaway greenhouse warming that melted the ice rapidly. Some researchers argue the evidence supports multiple such events. Others dispute how complete the freezing was. But even a partial snowball Earth would have created conditions almost incomprehensible by modern standards, and life somehow survived, sheltering perhaps near volcanic vents beneath the ice, waiting for the thaw. The Cambrian explosion is one of the most extraordinary and puzzling events in the history of life. For most of Earth's history, life was microbial or simple and soft-bodied, leaving very little in the fossil record. Then, about 538 million years ago, within a geologically brief span of perhaps 20 million years, the fossil record suddenly fills with a spectacular variety of complex animals, many with hard shells, eyes, legs, and body plans that represent the ancestors of nearly every major animal group alive today. Trilobites, ancient relatives of crabs and insects, became one of the most successful groups ever. Extraordinary creatures with body plans unlike anything living today appeared and disappeared within this brief window. The causes of the Cambrian explosion are still debated. Possibilities include a rise in oxygen levels finally reaching a threshold that allowed larger, more active animals to sustain their metabolism. Changes in ocean chemistry may have made it easier to build shells and skeletons. Or ecological interactions like predation may have driven an arms race of body-plan innovations. The Cambrian explosion is a reminder that the history of life is not a smooth, gradual progression. It has moments of sudden, cascading change that permanently and irreversibly alter the world. The Earth's axial tilt gives us seasons, and small changes in that tilt have driven ice ages. Earth's axis is currently tilted at about 23.5 degrees relative to its orbit around the Sun. This tilt means that as Earth orbits, one hemisphere leans toward the Sun for part of the year and away from it for the other part, producing the cycle of seasons. But the tilt is not fixed. It varies between about 22 and 25 degrees over a cycle of roughly 41,000 years. The shape of Earth's orbit also changes, becoming more or less elliptical over cycles of about 100,000 years. And the direction the axis points wobbles slowly like a spinning top over a cycle of roughly 26,000 years. Together, these three rhythms, called Milankovitch cycles after the Serbian scientists who described them, alter how much sunlight reaches different latitudes at different times of year. When the cycles align in ways that reduce summer sunlight at high northern latitudes, snow can persist year-round, reflecting more sunlight and triggering an ice age. The evidence of these cycles is preserved in ocean sediments and ice cores, and it confirms that Earth's climate has been pulsing in and out of ice ages with rhythm driven by subtle changes in the geometry of its orbit. Ice cores drilled from the ice sheets of Antarctica and Greenland contain a detailed record of Earth's climate stretching back hundreds of thousands of years. As snow falls and compresses into ice over thousands of years, it traps tiny bubbles of air. Those air bubbles are samples of ancient atmosphere, and by analyzing their composition, scientists can measure the concentration of carbon dioxide and methane at the time the ice formed. Dust layers record volcanic eruptions and dry periods. Isotopes of oxygen in the ice itself reflect the temperature at which the snow formed. The result is a layered archive, with each year's snowfall preserving a chemical snapshot of the climate at that time. The deepest ice cores from Antarctica span more than 800,000 years, covering 8 complete glacial cycles. They show clearly that carbon dioxide levels have tracked temperature through all those cycles, rising during warm interglacial periods and falling during ice ages. The concentration of carbon dioxide in those ancient air bubbles never exceeded 300 parts per million throughout that entire 800,000-year record. Current levels are well above 400 parts per million and rising, a value that has no precedent in this archive and has not been seen on Earth for several million years. Permafrost covers roughly a quarter of the land surface of the Northern Hemisphere, and it holds secrets that have been frozen for tens of thousands of years. Permafrost is ground that remains frozen year-round, and in some regions of Siberia and northern Canada it extends to depths of hundreds of meters. Within this frozen ground, organic material from ancient plants and animals has been preserved for thousands of years without decomposing, because decomposition requires liquid water and microbial activity that the cold prevents. Woolly mammoths have been recovered from Siberian permafrost with their fur, flesh, and stomach contents intact, including the last meal they ate before they died. Seeds found in permafrost have been germinated after tens of thousands of years of frozen storage. Ancient viruses frozen in permafrost have been revived in laboratory conditions and shown to still be capable of infecting single-celled organisms. As the climate warms and permafrost thaws, two things happen. The organic material begins to decompose, releasing carbon dioxide and methane that have been locked away for millennia. And material that has been frozen since the Pleistocene is returning to conditions it has not experienced in a very long time. Permafrost thaw is both a climate feedback and an opening of an ancient archive, and what emerges from it continues to surprise researchers. The Sahara Desert was green and wet not very long ago in geological terms. Around 11,000 years ago, as the last ice age ended and Earth's orbital geometry shifted, the summer monsoon in North Africa intensified dramatically. Rain penetrated deep into what is now desert, filling lakes, sustaining rivers, and supporting a landscape of grasslands, woodlands, and wetlands across the region we now call the Sahara. Elephants, hippos, crocodiles, and giraffes live across areas that today receive almost no rainfall at all. Human populations spread across the region, leaving behind rock art depicting animals, people, and cattle herds in places that are now bare sand and rock. The period is called the African Humid Period, or the Green Sahara, and it lasted for several thousand years before the orbital forcing shifted again, the monsoon retreated, and the desert advanced. The transition was not always gradual. Some evidence suggests it ended relatively abruptly in some regions as vegetation loss accelerated drying in a feedback loop. The Green Sahara is a reminder that even the most extreme landscapes on Earth are not permanent features. They are states that the planet moves through and out of again over time, driven by forces that operate on scales longer than any human civilization. The Earth breathes in a rhythm that can be measured from space. Atmospheric carbon dioxide levels rise and fall by a few parts per million every year in a regular cycle. In the northern hemisphere spring and summer, the enormous area of vegetation there, forests, grasslands, and croplands, absorbs carbon dioxide through photosynthesis as it grows. Carbon dioxide levels in the global atmosphere dip measurably. In autumn and winter, as vegetation dies back and decomposition releases carbon, the levels rise again. This annual pulse is visible in measurements taken from remote monitoring stations far from any local sources or sinks, including stations on mountain peaks and in the middle of the ocean. It reflects the breathing of the land surface, primarily the northern hemisphere because it contains far more land mass and vegetation than the southern. The amplitude of the seasonal swing have been growing over the decades, and scientists interpret this as evidence that higher carbon dioxide levels and warmer temperatures are stimulating more vigorous plant growth. The planet is responding to the changes in its atmosphere, amplifying the signal. It is not just recording what is happening, it is participating in it. Though the long-term direction of that participation, whether it will act as a brake or as an accelerant, depends on factors still being studied. Life exists deep inside solid rock, far from any sunlight or surface chemistry. The deep biosphere is a collective name for the microbial communities living within rock and sediment kilometers below the surface of the Earth. These organisms were only confirmed to exist in the second half of the 20th century, and even now, quantifying them is difficult because reaching them requires expensive deep drilling. But samples from boreholes and deep mines have revealed microbes living in water-filled cracks in rock 2 kilometers or more underground, surviving on the products of chemical reactions between water and rock, hydrogen gas from the natural radiolysis of water, or the slow seepage of organic carbon from ancient buried material. Some of these organisms may divide only once every few thousand years, living at a pace so slow that a human lifetime would not register as a meaningful interval in their existence. The total biomass of the deep biosphere is uncertain, but may be comparable to or even greater than the total biomass of all life on the surface. If that estimate is correct, then the majority of life on Earth, by mass, has never seen the sun and never will. Life on this planet is not just a surface phenomenon. It reaches into the rock itself, quietly existing in the dark on the slowest possible schedule. The rocks themselves cycle through the Earth on a timescale of hundreds of millions of years. At the surface, rocks are exposed to weathering, broken down by rain, wind, frost, and the slow chemical action of water and organisms. The fragments are carried by rivers to the ocean, where they settle as sediment and gradually compress into sedimentary rock. Where tectonic plates collide, some of this rock is pushed up into mountain ranges. Where plates subduct, rock is dragged down into the mantle, where it melts and eventually returns to the surface through volcanoes as igneous rock. Heat and pressure deep in the crust can also transform existing rock into metamorphic rock without fully melting it. This cycle, which moves material from the surface into the Earth and back out again, is one of the processes that regulates the planet's carbon budget over geological time. Carbon locked into limestone on the ocean floor is eventually subducted and releases carbon dioxide through volcanism, while weathering of surface rock consumes carbon dioxide from the atmosphere. The balance between these processes has kept the planet within a habitable range for most of its history, though with very large swings in climate along the way. The rock beneath your feet is not inert. It is material in transit, on a journey measured in geological time. The Kola Super Deep borehole in Russia is the deepest hole ever drilled into the Earth, and what was found that surprised everyone. Beginning in 1970, Soviet scientists began drilling a borehole on the Kola Peninsula in northwestern Russia as a scientific experiment to see how deep they could reach and what they would find. After 20 years of drilling, they reached a depth of 12 kilometers, the deepest point any humans have ever directly sampled. At that depth, the rock was expected to be dry and dense. Instead, scientists found that the rock was saturated with water. The water had not percolated down from the surface, but had been produced by chemical reactions within the rock itself, squeezed out of minerals by the enormous pressure. Microscopic fossils of single-celled organisms were found in rocks 2 billion years old at depths far greater than anyone expected life to have penetrated. The temperature at the bottom was around 180 degrees Celsius, much hotter than predicted, which is one reason drilling eventually had to stop. The borehole is now sealed, but what it revealed changed assumptions about what the deep crust is like. Even our most ambitious attempt to reach the interior of the Earth barely scratched the surface. The distance to the center remains 12 times deeper than the deepest hole we have ever made. Earth's gravity is not perfectly uniform across the surface. It varies slightly from place to place depending on the density of the rock below and the local topography. A mountain of dense rock will pull slightly harder on a gravimeter than a region underlain by less dense material or a large underground cavity. These variations are small, but sensitive instruments can detect them clearly. Satellites have been used to map the global variations in Earth's gravitational field in fine detail, producing maps that reveal the density structure of the crust and upper mantle. These maps show the fingerprint of ancient geological features, subducted slabs still cooling deep in the mantle, the thick roots of old cratons that have not moved in billions of years, and the places where the crust is thinner over hot and rising material. Gravity anomalies have also been used to find buried craters, ancient sedimentary basins, and even archaeological sites by detecting the contrast between disturbed soil and undisturbed bedrock. The fact that gravity varies also means that you weigh very slightly more at the poles than at the equator, partly because you are closer to the center of the planet and partly because of the centrifugal effect of Earth's rotation. The ground pulls on you, but it does not pull everywhere quite equally. The aurora is one of the most beautiful atmospheric phenomena on Earth, and it is produced by the same shield that protects all life here. When charged particles from the solar wind are deflected by Earth's magnetic field, most pass around the planet. But near the poles, where the magnetic field lines curve back into the planet, some particles are guided down into the upper atmosphere. There they collide with atoms and molecules of nitrogen and oxygen at altitudes of roughly 100 to 300 kilometers, exciting those atoms and causing them to emit light as they return to their ground state. Oxygen at different altitude produces different colors, green at lower levels and red high up, while nitrogen contributes blues and purples. The patterns, called curtains, rays, and dancing ribbons of light, shift as the flow of particles from the sun fluctuates and as the magnetic field moves and flexes. During strong solar events, auroras can be seen far from the poles, sometimes reaching into the middle latitude of Europe and North America. Ancient peoples developed many explanations for the aurora, including spirits, fire foxes, and the reflections of armies marching in distant lands. The scientific explanation is no less extraordinary. The sky itself is illuminated by the planet's invisible protective field interacting with the sun's continuous breath. The ozone layer protects the surface of the Earth from ultraviolet radiation, and its discovery and near destruction is one of the most significant environmental stories of the 20th century. Ozone is a molecule made of 3 oxygen atoms rather than the usual 2, and it is concentrated in a layer of the stratosphere between about 15 and 35 kilometers altitude. It absorbed the majority of the sun's ultraviolet B and C radiation, which would otherwise reach the surface in quantities sufficient to cause widespread damage to DNA in living cells, suppressing immune systems in animals and inhibiting photosynthesis in plants. In the 1970s and 80s, scientists discovered that synthetic chemicals called chlorofluorocarbons, used widely in refrigerants and aerosol sprays, were reacting with ozone in the stratosphere and destroying it. A hole in the ozone layer appeared over Antarctica each spring, larger than the continent of North America. The discovery prompted one of the most successful international environmental agreements in history, the Montreal Protocol, signed in 1987, which phased out the production of these chemicals. The ozone layer has been slowly recovering since then, and is projected to return to pre-industrial levels by the middle of this century. It is a rare example of a global environmental problem being identified, addressed, and reversed within a human lifetime. Jet streams are rivers of fast-moving air high in the atmosphere, and they shape weather patterns across entire continents. Jet streams form at the boundary between cold polar air and warmer air from lower latitudes, typically at altitudes of around 9 to 12 kilometers in the upper troposphere. They can reach speeds of over 300 kilometers per hour and extend for thousands of kilometers in length. Aircraft flying west to east at those altitudes can catch a jet stream and shorten their journey significantly, while those flying east to west must route around them to avoid severe headwinds. But jet streams also guide the path of weather systems at the surface, steering storms and determining whether a given region experiences a week of rain or a week of sunshine. The position and strength of jet streams varies seasonally and from year to year, and there is evidence that climate change is affecting their behavior. A warming Arctic reduces the temperature contrast that drives and constrains a polar jet stream, which may allow it to wander more widely in large meanders. When the jet stream dips unusually far south, it can drag Arctic air deep into lower latitudes, producing extreme cold events in places that normally experience mild winters. The rivers of air above us are as consequential as any river on the surface, and they too are changing. El Nino and La Nina are not just weather events in the Pacific. They reshape weather patterns across the entire globe. Under normal conditions, trade winds blow across the tropical Pacific from east to west, pushing warm surface water toward Asia and Australia, and allowing cold, nutrient-rich water to well up along the coast of South America. Every few years, these winds weaken or reverse, and the warm water spread back across the central and eastern Pacific. This is El Nino. The changed distribution of ocean heat alters the atmosphere above it, shifting rainfall patterns across the tropics and beyond. Droughts that would normally affect Australia and Southeast Asia arrive. Unusual rainfall and flooding affect parts of South America. The Indian monsoon can be disrupted. Even regions as far away as East Africa and the southern United States feel the effects through changed storm tracks and precipitation. La Nina is the opposite phase, with stronger than normal trade winds and cooler than average Eastern Pacific temperatures, and it brings roughly opposite effects. The cycle repeats irregularly every 2 to 7 years and is one of the most powerful drivers of year-to-year climate variability on Earth. Understanding it well enough to predict its onset months in advance has enormous practical value, and improving those predictions is an active area of climate research. The formation of coal tells a story about a time when forests covered the world, and nothing yet knew how to decompose wood. The vast coal deposits that powered the Industrial Revolution and still fuel electricity generation today were formed primarily during a period called the Carboniferous, roughly 350 to 300 million years ago. At that time, large forests covered much of the land surface, with trees that could reach 30 meters tall producing wood reinforced by a compound called lignin. When these trees fell, they did not decay the way wood decays today. The fungi and bacteria that break down lignin had not yet evolved, or had not yet spread widely, so the fallen would accumulate in enormous quantities in swampy environments, layer upon layer, over millions of years. Compressed and heated over geological time, this material became coal. The irony is that the coal we burn today is made of carbon that was captured from the atmosphere over tens of millions of years by ancient forests, and burning it returns that carbon to the atmosphere in centuries. The Carboniferous forests pulled enormous quantities of carbon dioxide out of the air as they grew, contributing to a cooling of the climate and possibly to one of the ice ages of that period. The fuel we use to power modernity is a compressed body of a world that no longer exists. A natural nuclear reactor operated inside the Earth in Africa 2 billion years ago, and it ran for hundreds of thousands of years without human involvement. At a site called Oklo in what is now the country of Gabon, geologists discovered in 1972 that uranium had at some point in the distant past undergone a sustained nuclear fission chain reaction, exactly as in a human-built nuclear reactor, but powered entirely by natural conditions. 2 billion years ago, the proportion of fissile uranium in natural deposits was higher than it is today because radioactive decay had not yet had as long to reduce it. At Oklo, the geometry of the deposit and the presence of groundwater acting as a moderator to slow neutrons allowed a chain reaction to begin and sustain itself. The reactor appears to have operated in pulses, running for about 30 minutes at a time and then shutting down as a water moderator heated up and boiled away, then restarting as it cooled and returned. It continued in this on-off cycle for hundreds of thousands of years before the fissile material was depleted. The discovery confirmed predictions about nuclear reactor physics and also provided unexpected information about how Earth's geology behaves over deep time. Nature solved the nuclear reactor problem 2 billion years before we did. The animals that navigate by the Earth's magnetic field are doing something we still cannot fully explain at the molecular level. Many species, including migratory birds, sea turtles, salmon, monarch butterflies, and sharks, are known to use Earth's magnetic field for navigation. Sea turtles hatched on a beach in Florida navigate across the Atlantic Ocean and back over decades, returning to within kilometers of the beach where they were born. Migratory birds cross continents and oceans in the dark, maintaining compass headings that are adjusted for the local variations in the magnetic field with precision that suggests a detailed internal map. The mechanism by which they sense the field is not entirely clear. One leading hypothesis involves a protein called cryptochrome found in the eyes of birds, which may undergo quantum mechanical reactions that are sensitive to the direction of the magnetic field, essentially giving the animal a compass built from chemistry. Another mechanism involves tiny crystals of magnetite, a magnetic mineral, found in the tissues of various species. It is possible that different animals use different mechanisms, and that the ability to sense magnetic fields has evolved independently multiple times, just as flight and vision have. The navigational feats these animals perform are extraordinary. The mechanism behind them is still being decoded. The Earth's rotation is gradually slowing down, and the day is getting longer. Tidal friction between the Earth and the Moon is the primary cause. As the Moon's gravity pulls on the Earth's oceans, it creates a slight bulge of water that is dragged slightly ahead of the Moon's position by Earth's rotation. The gravitational interaction between this bulge and the Moon acts as a brake on Earth's rotation, very slowly transferring angular momentum from Earth to the Moon. As a result, the Moon is slowly moving farther from the Earth, and Earth's rotation is gradually slowing. The effect is tiny, about 1.4 milliseconds added to the length of each day every century. But over geological time, the accumulation is significant. When the Moon formed, the Earth rotated much faster, and a day may have been only about 6 hours long. Ancient coral fossils preserve a record of daily and annual growth rings, and by counting them, scientists have estimated that hundreds of millions of years ago there were more than 400 days in a year, each shorter than today. The Moon is currently about 384,000 kilometers from Earth, and is receding at roughly 3.8 centimeters per year. Eventually, if the solar system lasts long enough, the Moon's recession and the slowing of Earth rotation would result in the two bodies becoming tidally locked, as many moons around other planets already are. Caves and karst landscapes are among the most hidden and extensive environments on Earth. Karst forms when water, made slightly acidic by dissolving carbon dioxide from soil and atmosphere, slowly dissolves limestone rock over thousands to millions of years. The result can be a landscape full of sinkholes, disappearing rivers, and underground cavern systems of extraordinary complexity and scale. Mammoth Cave in the United States has over 650 kilometers of mapped passages and is the longest known cave system on Earth, yet exploration continues to find new sections. Cave systems in Vietnam and Malaysia have individual chambers large enough to contain entire city blocks under their ceilings. Cave preserve records of past climate in the form of stalactites and stalagmites, which grow in layers whose chemistry reflects rainfall patterns and temperature at the time each layer was deposited. They also harbor specialized ecosystems of organisms adapted to permanent darkness, low nutrients, and high humidity. Cave fish that have lost their eyes over evolutionary time, translucent crustaceans, and specialized fungi represent evolutionary experiments shaped by isolation over millions of years. Caves are also records of human prehistory, preserving art, tools, and bones in conditions that surface sites rarely match. The underground world beneath the familiar landscape is vast, connected, and in many places still entirely unknown. The deep carbon cycle moves carbon between the surface and the interior of the Earth on timescales of hundreds of millions of years, and it has been a fundamental regulator of climate throughout Earth's history. Carbon enters the deep Earth when carbonate rocks and organic material are carried down into the mantle by subducting tectonic plates. In the heat of the mantle, this carbon is incorporated into minerals or releases carbon dioxide and methane, which eventually return to the surface through volcanic activity. At the surface, carbon dioxide from the atmosphere react with rain and rock in the process of chemical weathering, forming carbonates that are eventually deposited on the ocean floor, from where the cycle begins again. This geological carbon cycle operates on timescales of tens to hundreds of millions of years, far slower than the biological carbon cycle driven by photosynthesis and respiration. Over the history of the Earth, the deep carbon cycle has played a role in ending snowball Earth conditions, moderating the effects of large volcanic events, and gradually drawing down atmospheric carbon dioxide as the sun has slowly brightened. Without it, the accumulation of volcanic carbon dioxide would likely have pushed surface temperatures to extremes incompatible with liquid water. The inside of the Earth and the atmosphere are connected in a slow chemical conversation that has been going on since the beginning. Microbes outnumber every other form of life on Earth by an almost incomprehensible margin, and they carry out chemical reactions that make the surface habitable. The total number of microbial cells on Earth has been estimated at somewhere around 10 to the power of 30, a number so large it has no intuitive meaning. They live in soil, in water, in rock, in ice, in hot springs, in the deep ocean sediment, and inside every multicellular organism on the planet. The human body alone contains roughly the same number of microbial cells as it does human cells, and those microbes perform functions ranging from digestion to immune system regulation that we depend on without being aware of. At the planetary scale, microbes drive the cycling of nitrogen, which is an essential component of proteins and DNA, and which most plants and animals cannot access from the air directly. Nitrogen-fixing bacteria convert atmospheric nitrogen into forms that can be used biologically, and without them the fertility of the soil would collapse. Microbes also drive the sulfur cycle, the iron cycle, and the cycling of many other elements. They are not just passengers in the Earth system. They are operators of many of its most fundamental processes. If all microbes disappeared overnight, the planet's chemistry will begin to unravel within a matter of days. The thickness of the Earth's crust varies enormously from place to place, and those variations tell us a great deal about the forces that shape the surface. Under the oceans, the crust is typically only 5 to 10 kilometers thick and made of dense basaltic rock formed at mid-ocean ridges. Under the continents, the crust is much thicker, averaging about 35 kilometers and reaching up to 70 or more kilometers beneath major mountain ranges. The reason for this difference is partly compositional, as continental crust is made of less dense rock than oceanic crust, and partly dynamical, as the forces that build mountains and subduct plates produce different thicknesses in different tectonic settings. Where the crust is thick, it floats high on the underlying mantle, producing elevated terrain. Where it is thin, the surface sits lower. This principle, called isostasy, means that mountain ranges have deep roots extending down into the mantle, much like an iceberg has most of its bulk below the waterline. As mountains erode, the roots gradually rebound upward, a process called isostatic rebound, which means erosion can go on for far longer than the mountain's original height would suggest. After the ice sheets of the last ice age melted, the crust beneath Scandinavia and Canada began rising and is still rising today, released from the weight of ice that had pressed it down for tens of thousands of years. The future of the Earth is already partly written in physics, and it involves the sun. Over the next several billion years, the sun will gradually brighten as it fuses hydrogen in its core. The increased energy output will warm the Earth's surface over geological time, eventually pushing conditions beyond what liquid water can sustain. Models suggest the Earth's oceans may begin to evaporate within about 1 to 2 billion years as the sun's output increases enough to trigger a moist greenhouse effect. Water vapor, itself a greenhouse gas, would accelerate warming once it begins to dominate the upper atmosphere, leading to further evaporation in a runaway process that may ultimately strip the oceans entirely. Venus is thought to have undergone a similar process, which is one reason its surface is now a dry, crushing inferno. In about 5 billion years, the sun will exhaust its hydrogen fuel and expand into a red giant, large enough to possibly engulf the Earth's current orbit, though Earth's orbit may have shifted by then due to the sun's loss of mass. What remains after that would be a white dwarf sun and, if anything of the Earth survived, a cold, airless rock orbiting in silence. The same forces that gave birth to this planet will eventually claim it. The story has a beginning, a long and complex middle, and an ending already set in motion. The water that makes Earth a blue planet may have arrived from space. Earth formed in a part of the solar system that was warm enough that much of the original water in the planet-forming material would have been lost to space during the violent early phase of accretion. Yet Earth has an enormous amount of surface water. One leading explanation is that much of this water was delivered later by asteroids and comets from the outer solar system, where water ice was stable. The composition of Earth's water, particularly the ratio of ordinary hydrogen to its heavier cousin deuterium, is consistent with carbonaceous asteroids having contributed significantly. These asteroids may have bombarded the inner solar system heavily during a period called the Late Heavy Bombardment, around 4 billion years ago. Comets also carry water ice, but the deuterium ratio in comets from the outer solar system often does not match Earth's water as closely, suggesting asteroids are the primary source. Some of Earth's water may also have been present all along, trapped in the minerals of the original rock as the planet formed and released later through volcanic activity. The question of exactly where Earth's water came from is still being refined as new measurements are made of asteroids and comets, and each measurement adds a small piece to a very old puzzle. And so we drift slowly back from the depths of geological time, carry with us the quiet weight of everything the Earth has seen. We traveled from the fiery, collision-filled birth of the planet to the patient churning of the mantle beneath our feet. We listened to the magnetic field humming quietly in space, deflecting the sun's breath day after day for billions of years. We watched continents drift and collide, mountains rise and wear away, oceans appear and disappear in the rhythm of tectonic time. We stood at the edge of the Cambrian explosion and watched complexity appear as if from nowhere. We felt the cold of snowball Earth and the heat of ancient volcanic winters. We breathed the oxygen given to us by microbes that lived long before any animal ever existed. We descended into the deep rock and found life still waiting there in the dark, patient and slow and utterly alien to the surface world above. We looked forward to a future where the oceans evaporate and the sun expands, and found that even that distant ending is not called for restlessness, but for certain quiet wonder at how long this world has held together and how much it has carried and survived. The Earth is not a backdrop to life. It is alive in its own way, restless and changing and ancient beyond reckoning, and you are standing on it right now. If you enjoyed this sleepy journey, you can support the channel by liking, subscribing, or leaving a calm little comment before you rest. It helps more curious minds find their way here. And if you are still awake, there is another video waiting on your screen, ready to carry you onward into another corner of science. But for now, let the questions loosen their grip. Let your shoulders soften. Let your jaw unclench. Allow your breathing to slow, steady, and deepen. Picture yourself lying on warm ground on a clear night, the whole weight of the Earth beneath you, solid and ancient and holding you gently. 4.5 billion years of history in the rock below your back. You do not need to understand it all tonight. You only need rest. Sleep well, and good night.